today we will start with the topic on industrial drive system. In this industrial drive system, in this course, we will be mostly concentrating on the electric drive part. So, we will be talking about the electric drive part. A basic definition of an electric drive system can be: an electric drive is defined as a form of machine equipment designed to convert electric energy into mechanical energy and provide electrical control of this process. So, let us write that one, electric drive. And electric drive is defined as a form of machine equipment designed to convert electric energy electrical energy into mechanical energy. Energy into mechanical energy. So, in an electric drive, what we are doing? We are trying to convert electrical energy into mechanical energy and provide electrical control of this process or electronic control of this process. That means, when we convert electrical energy into mechanical energy, so the load, the output system required in a particular fashion. So, we require a necessary control of the system. So, all the control nowadays we do it with electronics control. So, we will say to convert electrical energy into mechanical energy and provide electrical control of this process. Electrical control of this process. This is very essential. We are converting electrical energy to mechanical energy with the necessary control. So, this is the basic definition of an electric drive system. Now, this definition I have taken from a very famous Russian book by Professor Chilikin, and I feel that is a very good definition of an electric drive system. Now, based on this definition, let us form a block schematic so that we can clearly understand what is the conversion process, what are the blocks inverts, and where the control. For control, what are the inputs required. So, basic block diagram let us write about. Now, the basic block diagram for an electric drive system will look like this. So, we are converting electrical energy into mechanical energy. So, we should have the source, what we call the power source. Power source, we will put it like this. This is the power source. This is the power source. Now, this power source, our basic power source are our mains. It will the voltages and currents will be in AC. Sometimes the power source can be a battery, where the voltage and current are DC. Sometimes we can have solar power. Okay, so power source has to, the output of the power source should go to a power converter. Why? This power converter will, the output of the power converter bring the power source to the required level, the voltage level, current level, frequency level as required by the load. So we require a power converter where the power source can be controlled and modified or changed AC to DC, whatever it is. So power converter, we will come to each block. So power converter. We are converting electrical energy to mechanical energy. The source and the power converter convert to the desired level, and for any mechanical energy we should require a motor. In electrical drive system, a motor is a part of motor, and motor will be connected to the load. Okay, this is the basic open loop block schematic of an electric drive. You have the power source, power converter will convert to the required level and give to the motor. Motor will give the required speed and torque to the load. So in our electric drive system, what we are controlling, conversion of the electrical energy to mechanical energy means the source is electrical and the load is mechanical. So we are converting into electrical energy to mechanical energy. That means basically speed and the torque. Now we are in our basic definition, we said we should give the necessary control of this process. So let us have a block diagram like this. Controller, that is our electronics controller. Now controller output will control what? We do not have any control of the power source. Power source is what is available to us, given to us. Okay, and load is suggested by the customer, what he wants. So once we select the motor, then all the control, motor parameters we cannot change. We have to control the whole thing through our power converter. So controller output will mainly go to the power converter. So to take the necessary control action, controller requires some inputs. So as many as inputs are always good for a good controller, but the more input means more devices, more sensing equipments are required. Then the system will become very costly. So the controller input depends on a cost-effective design. We will limit to the what is bare minimum required. So controller input can be from power source. Why from power source? Suppose if our AC, our mains, we are using as the power source. Sometimes the voltage can fluctuate, frequency can fluctuate. Then the power converter should control it such that the motor motor gets the required steady voltage and current, irrespective of the fluctuation in the power source. So there is a input from the power source is required. We can also have input from the motor. Speed can be one input. Motor voltages and current can be one input. Suppose due to some sudden change in load, motor drives very large current which is beyond its requirement. Suddenly we can control that one through our power converter. Through power converter we can control the motor input parameters such that the current can be controlled. Or sometimes the load required more torque, it is rotating. So motor should drive more current. So this can be controlled through our power converter. So the basic inputs we can have power source and from the motor load and the power converter. This is the basic block diagram of an electric drive system. Now in our course we will be mostly studying the power converter side and the controller. Why? Because as a design engineer we have only access to these two. We can only control, and we can select and choose these two, and motor is selected or decided based on the load requirement. Once these are selected, these are fixed. That means power source, motor and the load. Then any control parameter we can only control through this power converter and the controller. This is only in our control. Okay. Now, let us again go to a further definition of our power converter. What is the conversion process happening here? So let us take the power source. Power source can be, we can basically, we can specify as DC and AC. AC. So we will go to the next page. Depending on the power source available, either battery or mains, power source can be basically defined as basic form DC or AC. Now, our output of the converter also we can very basic, with the basic form of output we can say either DC or in AC. So here also there is a power converter, DC or AC. Now we should have conversion. The power converter convert the power source, a DC voltage of one level should convert to a voltage level to a different voltage level as required by the motor. So there is a DC to DC conversion. This has to be achieved through our power converter. So basic DC to DC power converter, you know it is an it is an SMPS, switched mode power supply, SMPS, switch mode power supply. One example. Then DC to, then AC to DC. That is our mains. That means AC power source with alternating voltage and current, we are convert to a DC voltages and current. The basic power converter of this one we can call as the rectifier. Rectifier. But if you see in electrical, as an electronics engineer or electrical engineer, we know how to rectify. If you have the diode, a three-phase or single-phase rectification is possible. But we will not be, this is not the required rectifier what we want. Why? We require control of the process. So what we require here into is a controlled rectification, like using thyristors, phase control converters. Okay. So one example. So it is controlled rectifier. This is controlled rectifier. That is AC to DC. Then the next conversion, this is power source. This is on the load side or the motor side. DC to AC, that means a DC source, battery, or a rectifier output. That means what is available to us a DC source, but we want AC. AC means, one example is UPS, that is basically inverters. These type of converters are called, power converters are called inverters. These are called inverters. We will be studying in the due course the basic, the control of the inverters, various inverter topologies for speed control applications. We will be concentrating more on that one later. Then another one, AC to AC. That means voltage, current and frequency of one into another voltage and current and frequency of different level. These are basically in old books you can see one class of converters called cycloconverters, one example. But we will not be studying about this one now. We will be mainly concentrating the AC to DC and the DC to AC converter in our main course. Now, after going through the classification and block, we said our control of the whole process is through the controller. That means we have to design the controller such that the system will quickly adapt to the change without much transience. So, controller design is very important. Nowadays, simulation tools are available. So, we can have a mathematical study and we can simulate and we can tune the controller before a hardware implementation is started. Why? That will save lot of time and money. Otherwise, we have to learn from the failures. If the hardware, if keep on fail and if we learn from that process, the cost of the whole system will go up. So, a controller design and controller tuning before a controller design implementation, a controller design and tuning can be done through a simulation study. For a simulation study, the whole system should be modeled. So, that means equivalent mathematical representation of the system is required. That means the representation for the power source basically we can AC or DC we can do it, then the power converter, then the motor. So, a mathematical model of the motor required based on for our controller design. As I told you before, the whole process is converting electrical energy to mechanical energy. Mechanical energy through our, what is the output of the load? The mechanical energy, the torque and the speed. From there we are generating the energy. So, for motor, a basic input output relation, a torque speed characteristic is required. Torque speed characteristics required. That means various speed, what are the torque required. Then for the torque, what are the parameters you have to control at the input side of the motor. That is the voltage and current. For that voltage and control, corresponding controller has to be initiated for the power converters. Now, the basic load, that is the mechanical load, we can basically divide into that is the torque speed characteristics into basic 4 category. Let us take the torque speed characteristics of the load. 1. Torque independent of speed. Let us write the graph, torque speed characteristics of this load. The graph, this is our speed, that is speed in electrical radians per second, and this is the load torque. So, torque is independent of speed. So, the curve will be, the speed torque characteristics will be like this, steady. That means, irrespective of the speed, it will always generate constant load. So, what are the example for this one? Example, low speed hoisting, that is cranes during hoisting. During hoisting. That is one. Then, machine tool feed mechanisms. Feed mechanisms. These are some of the examples. Many examples you can find in many textbooks. I am giving some example. Then 2. Linearizing characteristics. What do you mean by linear rising torque speed characteristic? What do you mean by linearizing torque speed characteristics? That means whenever the speed changes, torque will also change proportionally. This is one. This is our second example. The torque speed characteristics for a linear rising low torque is like this. What is the example? Let us take a separately excited DC generator connected to a load of constant ohmic resistance. That is example. Separately excited DC generator connected to a load of constant ohmic resistance. That means a separately excited generator. The generator, that means machine is working as a generator, and the generator is feeding a load of constant ohmic resistance. Then let us see the torque speed characteristics is linearly rising. Now we know torque is equal to P by omega. Omega is the radians per second. The torque generated, the power developed by the generator divided by the speed give the torque. Okay. Now what is the power generated by the separately excited generator? P is equal to, that is the terminal voltage, into current I. Also we know that this V, the voltage generated by the separately excited DC machine is proportional to speed. That is proportionality constant K into omega. So V is proportional to K into omega. Why? We want to bring the basic relation between the torque and the speed. V is equal to K omega. And what is the current given out or taken by the load from the generator? I is equal to V by R. V is equal to proportional to speed K omega divided by the, this is our constant ohmic resistance R, K omega by R. So we got I. Now what is the power? In this is the basic equation. For this, in the basic equation, we require the power. Power is equal to P is equal to V into I. V into I is equal to, that we can substitute V and I. This will be equal to, when you substitute, K square omega square divided by R. Now let us substitute this one to this equation. Then what will happen? Torque is equal to K square by, this is a constant for a machine, this load is also constant. So the whole thing we can represent as by a constant K1, another constant K1. So this will be equal to K1 omega square, P we have substitute here, this part we are substituting here, divided by omega. Now this will be equal to omega square goes, this will be equal to, torque will be proportional to omega. So as the speed increases, torque also will increases, power will increase, torque will also increase. So this is the equation, linearly rising characteristics. Some simple examples I am telling here. Now let us look at non-linear rising characteristic. Let us go to the next page. Non-linear rising characteristic. Now the third example is non-linear rising, that is parabolic characteristic. Non-linear rising torque speed characteristic. torque speed, torque versus speed, speed characteristic. That is parabolic. How it will look? Non-linear rising, the speed, let us again draw the axis. This is our omega speed, this is our torque. So it will be something like this. Next, third characteristic. Previously the constant load speed characteristic, that was 1, linearizing was like this. This is the third one. Third one is this one. Most of the fan loads belong to this one. That means torque will be proportional to omega square. Most of the loads will be, most of the fan loads will come under this one. This is, see, constant, linearizing, then non-linear rising, then the next one will be for non-linear falling characteristics. Non-linear falling torque speed characteristic. How it will look? So, non-linear, here let us take a, that is torque is proportional to 1 by omega. This is non-linear rising, non-linear falling characteristics, that is something like this. This is 4. This is non-linear falling characteristics. Torque is proportional to omega. That means, or we can again say T into omega is a constant. Let us take in a rolling mill, one example, rolling mill. In a rolling mill, the paper comes out from the mill, the constant speed, okay, and it will be getting rolled to a drum. So paper is, this is the radius R. As the paper get rolled on to the drum, the radius keep on will increase. Now the paper is coming from the mill with a constant velocity, and we should take care of the speed of this drum has to be adjusted such that we have to keep constant tension. We have to keep a constant tension such that the paper should not, the paper should get rolled on to the drum properly. So what is the torque speed characteristic it shows? Now if you see here, the speed of rotation, what is the speed of rotation? Well, speed of rotation is distance by the speed b. So speed of rotation is equal to 2 pi r divided by b. This is the speed of rotation. This is second period, in seconds. Now if the speed, what we are attempting this equation, we have to get a torque speed, that is torque, and the speed, that's angular speed omega, we have to get a relation. Now what is frequency here? F is equal to, that is the frequency is equal to 1 by T. 1 by T is equal to V by 2 pi r. Okay, frequency we got. From once the frequency we got, we know omega. Omega is equal to 2 pi f. So, from the speed v, this v, we can get omega 2 pi f. Now, what is the power exerted by the drive? Power exerted by the drive, see, we have to give a constant force, opposing force here. This is force F. So, what is the power? Power is equal to, torque is equal to, the power exerted by the drive P will be equal to, that is F into R. R is the radial distance. F is the tangential force. The torque, this will give the torque. This is the torque. F into R. Torque into, what is omega? Omega is equal to 2 pi f. 2 pi f is equal to V by R from here. V by R. So, these two will cancel. F and V, these are constant for this one. So, power is constant. That means torque into omega, that is P, is equal to P is constant. Torque into power is equal to, that is P constant. That is, this will give constant horsepower load. These are some of the basic torque speed characteristics. Now, once we got the torque speed characteristics, let us take the combined system. This is the torque speed characteristics of the complete load. Okay. Now, in a combined system, there is a driving torque and the load torque. For speed control, this should be matching. So, how that driving torque has to be controlled to meet the load torque? That is our basic control purpose. So, let us take the combined system. Now, let us go to the next page again. That is a combined load torque characteristics. Combined torque speed, that is torque speed characteristic. Let us draw the axis. This is omega, this is T. Now, the load torque, that is not in your control. Load torque will keep on varying, and for a stable operating speed or speed in a speed control system, the driving torque should match the load torque. So, let us take the load torque, a typical load was something like this. That I have put it on the negative axis, because this is the opposing force, opposing torque. This I will put load torque. Now, let us take our motor, the speed torque carriage of our motor. Let it be something like this. That is our motor, driving torque, okay, for the motor. Now, in our speed control system, suppose that we have to operate, the system will come to a stable state where the load torque, approximately this point, load torque will be equal to the driving torque, okay. But the load torque can vary, that is not in our control. Load torque can vary means, suppose the speed varies, load torque goes here. What will happen? Load torque goes here means speed has changed. Now, this is the load torque demand by the load, but according to the motor characteristic, the driving torque, that is TD, is less than the load torque now. So, what will happen? System will slow down and come to this point. Now, let the load torque decrease. In this case, what will happen? At this point, the load torque is less than the driving torque. So, this will accelerate the system, it will come to the stable point. But in most of the cases, this is for a typical load speed characteristic. Is most of the cases, it will not come to a stable system. So that depending on the load torque requirement, our motor characteristic, torque speed characteristic, we have to control, we have to modify through our power converter. So, our whole control block, the purpose of the control block is to dynamically control the torque speed characteristic so that the driving torque will be always equal to the load torque as demanded by the load for a particular speed. So, such cases we require a closed loop control system. Now, as I told you before, see, I have so far only told you TL, load torque. So, load torque basically we can define as, or the driving torque PD is equal to the load torque, okay, TD, sorry, this is TD, this is TL, plus, if the speed is constant, driving torque will be equal to load torque. Suppose during acceleration and deceleration, there is more load, there is a torque change requirement or torque demand from the load. So, that can be explained as J into d omega by dt. J into d omega by dt, this approximately J is the moment of inertia. So, whenever acceleration deceleration is there, the total driving torque should be equal to the constant load torque plus the acceleration and deceleration. Now, how to find out for a particular load system, how to find out the J? There are various techniques available in literature. I will take one from the famous Leonard's book. What we have to do, the complete system under no load, you switch the machine to the full speed of drive the system to the full speed. Then full speed and find out the this is omega 0, this is ml, this is our time 2 axis. So, drive the system for various speeds of operation. 5-6 points you take it and drive the system and find out the load torque required. So, you plot the load torque, you go to the ml. Now, run the system to the full speed and switch off the power supply. Then what will happen? The whole system will decelerate. So, during the deceleration, what will happen? The driving torque is 0. So, the decelerating torque generated by d omega by dt will be opposed by the friction and windage loss. So, slowly the system will decelerate. So, at various point measure omega, you note the time and measure the omega. At various point measure the time and omega, and approximately at this point and time you can find out d omega by dt. So, d omega by dt we know the motor the system is under no load at various speeds. So, we know the at various speeds what is the driving torque. So, this driving torque at the no load torque. So, if you write the equation J into d omega by dt plus ml is equal to 0. So, because we have switched off the system and the system is decelerating. So, at various speed the J into d omega by decelerating torque is the no load torque of the system, that we can get from this one. So, from this equation d omega by dt we know, ml we know, we can approximately find out J. This is one way of doing the thing. That there are other techniques also available. This is a one simple way of finding out J. So, once you know the J, once the speed, then what we know? We know the approximately we can find out the torque speed characteristic of the system during acceleration also. Now, in this class, in this lecture, we have just basically the basic definition of the electric drive is introduced and basic block diagram is given. Then depending on the voltage source, either AC, DC and the output requirement, we have classified the power converter or conversion process into various 4 categories. Then the torque speed category of the machine, we have various categories: rising, constant, non-linear rising, non-linear falling. We have different typical example. Then we talked about the combined characteristics. Combined characteristics, what we found out, it is required to modify the motor load torque characteristics through our power converter, such that depending on the load variation, that is the TL, always we have to keep the driving torque equal to the load torque. So, there is a closed loop control system is required. Okay, the driving torque, the load driving torque is not only the steady state, during the acceleration and deceleration also we have to give the transient power also to the system. So, that the transient power, acceleration and deceleration depend on the moment of inertia of the system, and typically how to find out the moment of inertia, a typical system is also we explained. Now, let us go to the some of the basic power converter configurations. So, because we require the power converter, once we select the power converter, then only we can choose the control function. Then once we study some of the power converters, first we will study the power converters required for DC motor drive applications, then we will go for the inverters, that the power converter is required for AC motor drive application. Then how you design the closed loop control for DC motor and AC motor will be discussed during this course. For the DC motor, we will be mostly talking about the separately excited DC machine, because we will not have much time for all other cases. Separately excited DC motor, that is widely used for motor drive applications. Then the AC motor drive lectures, we will be talking about induction motor drive, mainly induction motor drive applications. During steady state, dynamic equivalent circuit model we will study. Then the simple V by F control, then the high dynamic and the controller like field oriented controller for high dynamic performance application will be studied later. Now, let us go to the basic power converter configuration. Let us go to the next page. Here, what we will be talking about the power converters, that is AC to DC converter for DC drive applications. So, controlled rectification is a must for this one. Let us study some of the basic power converter configurations. So, single phase, let us take a typical converter. Single phase, we will, before coming to the 3-phase rectification, control rectification, let us talk about single phase AC to DC power converter. The most basic single phase power converter is, the schematic is like this. Let us represent our mains like this. This is our controlling device. This is the thyristor. Then you have the load. Load I will simply represent it like this. It is inductive with the back EMF, can be there. So, we will have inductive plus back EMF load, that is a motor can be represented like this. Then it will go like this. Now, how do you control the output DC, that is DC this part? So, by at the appropriate point of the mains, we will be turning on the device and we will transferring the voltage to the load. So, by controlling the firing angle of the thyristor, we can control the output voltage. How it can be controlled? Let us see. This is our V0. What is the nature of V0 for a single phase with a single thyristor controller? How it looks? This is our mains. We will not be, whenever the, so for our present analysis, we will assume the control of the devices are instantaneous. We will not worry about the switching times involved in this one. So, the moment you give the gate pulse, thyristor will be turned on, and when the AC mains is getting, when the thyristor is, when the across the thyristor reverse voltage is applied, the thyristor will switch off immediately. So, let us say at this point we are giving the firing angle alpha. Firing angle will represent as alpha, alpha with respect to this point, the starting point of our mains here, zero crossing. Now, if the load is resistive, that is a symbol on the EC load. If the load is resistive, what will happen? The during this portion, the voltage will come across the load. During this portion, the voltage will come across the load. And if it is purely resistive load, then the current will also be instantaneously proportional to the voltage waveform. But pure resistive load is only a textbook concept. You will not have a pure resistive load. You will have resistive as well as inductive. So, pure, we will know in this class we will be talking about mostly on inductive loads and with the back EMF load also. So, with inductive load what will happen? So, before coming to the inductive load, let us say how for the resistive load, how the current it will be. Current will be in this form. Exactly, this will, that will be, this is our V in. During this portion, this any value of the current I0 will be equal to V in divided by R. But during the half cycle, the moment the voltage go negative, what will happen? There is a reverse voltage across the thyristor, anode and cathode. The thyristor will be immediately switched off. So, during this portion, the output voltage is, there is no voltage, instantaneous voltage across the load is 0 for a resistive load. Then, next half cycle again this will appear. This is the current, this is the voltage. So, we will see a pulsed waveform will be coming across the load. In this pulsed waveform, it will have the DC value and the AC value also will be there. High frequency AC value will be there. So, we will not talk about, but we are worried more about the DC value. So, what is the DC value? That is a V0, average value of this pulsed waveform. That can be easily find out. V0 alpha will be 1 by 2 pi, that is average value, integrating alpha to pi. This is our pi. So, alpha to pi will integrate and divide by the period, you will get the average value. So, this will be equal to Em sin omega t divided by dm. This we are integrating. Sin omega t when you integrate, what will happen? You will get minus cos omega t, integrating limit is alpha to pi. So, when you substitute this one, finally the V0 alpha will be, alpha is equal to Em by 2 pi into 1 plus cos alpha. Here alpha can be varied from 0 to pi. When alpha is equal to pi, what will happen? Cos pi, that is minus 1, output voltage will be 0. The DC value will be 0. When alpha is equal to 0, what will be the output? Alpha is equal to 0, the output will be alpha is equal to 0. V0 is equal to Em by pi. This is the output. And alpha is equal to 0 means we are firing the thyristor at the 0 crossing, the positive 0 crossing. What it says? It says this can be replaced by a diode then. So, output DC voltage for a single phase half bridge rectifier with a single diode is equal to Em by pi. Okay. But if you see here, during the negative part, we are not drawing any power from the mains. That means even the power source is there, we are not fully utilizing the power source. So, even though in the textbook these type of AC to DC converters using diode or thyristors are available, this only for the understanding that one, how to get the DC value. So, this value what we talked about, this is the DC value. But along with this value, because of this variation, you have the ripple content also will be there. So, that ripple content, that ripple voltage will produce its own ripple current, that has to be suppressed by the load. But we will not be putting any extra filters to suppress this one. To put filter means it is a cost effective proposition. So, inductive loads, as the frequency, high frequency of the voltage waveform there, the impedance of the load, that is L omega will increase, and the voltage divided by L omega, the current will, the high harmonic current can be suppressed. So, harmonic current, the amplitude of the high amplitude harmonic current can be suppressed only by through the motor inductance. But what we are interested is the DC part. So, that this value give the DC value. So, this will be it will be seldom used with the never used for any applications, okay, but for understanding it is available in textbook. So, whole analysis what we have done for a resistive load. So, this is for resistive load with the firing angle control. Now, let us see, instead of resistive load, what if we put a inductive load? Let us go to the next page. In the case of inductive loads, again let us draw our block schematic of the AC to DC converter with the firing angle alpha. Alpha can be varied from 0 to pi. Now, we have the highly inductive load. If we use here, what is the type of ripple voltage appearing across this one? V0T. That is a ripple, this VDC plus the ripple. Here this is our VM. If you see here, this is our voltage waveform. Alpha is fired here, firing angle is fired from here. Now, what happened? Because of the inductance, previously when the resistive load was there, the waveform, this ripple, the current waveform across the resistance was, the nature of the current variation was exactly same like the voltage variation. But here in this case, what will happen? The current waveform will be starting at this point, because current through the inductance cannot change instantaneously. So, what will happen? The current will vary like this. At this point, when the voltage is equal to 0, there is a current in the inductance. So, thyristor cannot switch. So, current through the inductance cannot be changed instantaneously. So, what will happen? Voltage will go negative. Voltage will go negative, the thyristor is conducting. So, whole voltage has to be suppressed across the inductive load. What will happen? At this point, inductance, the rate of change of current, it will go negative. So, that the voltage become, instead of positive negative here, it will become positive and negative. Here it have the input voltage has changed. So this rate of change of current will the load will take care of such that the rate of change current is just sufficient to forward bias the thyristor here, and current will keep on continuing, and this current will be from the stored energy till the stored energy is released, current will keep on coming. So what is the disadvantage here? During the negative portion up to this point also the voltage has appearing across the load. Now compared to our previous equation, firing angle and the DC is we cannot apply here because the negative portion also has come here. So the previous equation of alpha with respect to the output DC with respect to firing angle is no more valid here, because the thyristor is conducting in the negative direction also. Then how to avoid this negative portion? At the same time we have to give a freewheeling path for the inductance. This is during this portion it is called during the current conduction in the negative portion also we should give an alternative path for the inductance. At the same, this negative voltage should not appear across the load, such that the previous equation, that is V0 alpha is equal to Em by 2 pi into cos phi 1 plus cos alpha is valid. How to come to that one we will come in study in the next class.